In this module, we'll talk about light and the parameters for visual stimulation. We see an object when it reflects light, which travels through our eyeballs and activate receptors in our retina. The activation pattern of the retina sends signals to the brain, which is then interpreted as sight. Light is made up of different waves, which can be described by their wavelengths or hues. Light of specific wavelengths are related to specific colors. The human eye only sees a small range of wavelengths. This range of visible light is between 400 to 700 nanometers, with purple-violet in the 400 nanometer range and red in the 700 nanometer range. Beyond violet light, there's a spectrum of ultraviolet, X-rays, gamma, and cosmic rays, which have very, very short wavelengths and are not visible to the human eye. At the other end of the spectrum, beyond the red that we can see, are the infrareds, the microwaves and radio waves, which all have very long wavelengths and also are not visible to the human eye. For light within the visible spectrum, besides their wavelength, they are described by a few other properties. The wavelength gives light its color, which is also called hue. Saturation refers to the purity of a hue. That is, whether there are several wavelengths mixed or a single wavelength only. Saturation gives a sensation of brightness or vividness to a color, with a pure saturation seeming more bright. Luminance refers to the actual brightness of the light and can be objectively measured with a luminance meter. The unit of luminance is candelas per meter squared. Luminance is important to control when acquiring VEPs, as a lower luminance, that is a less bright stimulus, will result in a lower amplitude, longer latency VEP response. This means that we have specific luminance levels that we need for a VEP. Contrast refers to the difference in brightness or color that makes an object distinguishable from another object or from the background. This is important when acquiring pattern reversal or checkerboard VEPs, as low contrast stimuli will result in a poor quality VEP. That is, the amplitude will be reduced and the latency increased, because when there is poor contrast, it's hard to see the difference between the black and white checkerboard. Contrast is calculated as maximum luminance minus minimum luminance, all divided by the maximum luminance plus minimum luminance, all of this multiplied by 100 to make a percent. For a pattern reversal VEP, this is the luminance at the white square, the maximum luminance, minus the luminance at the black square, which is the minimum, divided by the luminance of the white square plus the black square, all multiplied by 100. When we acquire clinical VEPs, the hue that we use is either white light for a flash VEP or black and white hues for a pattern reversal VEP. We try to use as close to 100% saturation, as close to pure white or pure black as possible. The luminance and contrast are measured, and there are recommended values, which we will discuss in later slides. We will now talk about the types of VEP stimulation and their parameters. There are two typical types of stimulation used to evoke a clinical visual evoked potential. One is the flash stimulus, which is a full field light which activates most of the retinal area. This can be generated by either a photostimulator lamp or an array of LEDs built into goggles which are placed over the patient's eyes. The second way to generate the stimulus is through a pattern reversal stimulation, which primarily evokes the receptors in the fovea. The reversing checkerboard is typically presented on a computer monitor in a darkened room, with the patient being dark adjusted. The monitor has a known luminance, and the contrast of the black and white checks are adjusted to be greater than 50%. In addition to the type of stimulation, which will activate different parts of the retina, there are different sites of stimulation. Both eyes can be stimulated simultaneously to obtain a binocular VEP, or one eye can be stimulated at a time for a monocular VEP. Also, the two sides of the eyeball can be stimulated one at a time, and when both sides of the eyeball are stimulated together, this is a full field test, a full visual field test, or when one half of one eyeball is stimulated, that is a hemifield test. For example, in the far left diagram A, both eyes are stimulated and the entire retinal field is stimulated. And so this is a binocular full field study. In the next diagram B, both eyes are stimulated, but only the left visual field shows the pattern reversal stimuli. The right visual field is not receiving any stimulation. A left hemifield stimulation activates the right half or nasal half of the left eye retina, as well as the right half or temporal side of the right eye retina. Conversely, if the stimuli were presented to the right visual hemifield, it would activate the left retinal field of the left eye, also called the temporal field of the left eye, and it would activate the left retinal hemifield of the right eye, which is called the nasal field of the right eye. It's very easy to confuse hemifields and retinal fields. Thus, it's very important to be concise in labeling tracings and be very clear in letting the interpreter know which hemifields are actually being tested. In example C, the left eye is covered and only the right eye is stimulated with a full field stimulation. This is a right monocular full field test. In example D, the right eye is occluded and the left eye is stimulated. However, the stimulus is a left visual hemifield stimulation, which activates the nasal hemifield of the retina, also called the right retinal hemifield of the left eye. In addition to the properties we have just discussed, the other property that's important to note when acquiring VEPs is the size of the stimuli. To describe the size of a stimulus, we use a measurement called the visual angle. The size of an object's image on the retina is measured as an angle because the eyeball is round. The size of this angle, referred to as a visual angle, depends on two things. Firstly, the actual size of the object, and secondly, its distance from the eye. For example, a person standing close to the eye can take up a large amount of space on the retina and take up as much space as a very tall tower that's much further away. If the tower is moved closer to the eye, then its visual angle will increase as it will take up more space on the retina. By using visual angle to measure size, the real size of an object and its distance can be factored into the description of the object, and we know that if two objects are of the same visual angle, then they are activating the same size patch of retina. Visual angle, or theta, is measured in degrees with a protractor, and each degree can be further divided into minutes, where each degree has 60 minutes. When we acquire a pattern reversal VEP, there are recommended standards for size, and this is expressed as degrees and minutes of arc. In clinical VEPs, there are standard visual angles that are used to produce the clearest VEPs. Typically, the patient sits at least 70 centimeters and no more than 1 meter away from the monitor or screen. Pattern reversal VEPs are not consistently obtained at less than 7.5 minutes of arc. This is because if the stimuli are too small, the patient cannot see it properly, and the patient must be able to clearly see the borders of the checkerboard to obtain a good VEP. With normal visual acuity, normal VEPs are typically obtained with mid-sized checks And a good starting size is 24 to 32 minutes of arc for each check, and a field size, that means the size of the screen, of 6 to 12 degrees. If the clinical question involves a fovea, then smaller checks that activate primarily the fovea are preferred. A field size of more than about 2 degrees of arc starts to involve the periphery also, and so something smaller than 2 degrees of arc is preferred. If the patient has poor visual acuity or reports that they're unable to see or focus on the red dot, then larger check size can be used to determine whether there's a cortical visual response. Changes in check size must be clearly noted on the tracings for the interpreter. Quick check to see if you have correctly calculated a visual angle. The width of your thumb held at arm's length is approximately 2 degrees of arc, and this means that half your thumb is approximately 1 degree of arc wide. The figure in this slide shows how to approximate different visual angle sizes. Please continue to the next module, where we will do some actual visual angle calculations.